So let's get going. I think I recognize everybody that's on the call, but just in case you don't know who I am and who we are, I'm Tim Stone. I'm the president of the Twin City Amateur Astronomers Club, and we have decided this year as a board to try to do these kind of membership meetings. Back when I was a kid and I was in the Twin City Amateur Astronomers, every monthly meeting was a business meeting followed by a program. It was a talk of some kind given by one of the members or something like that, and we had social time. We'd sit around and talk and chat after the meeting was over and all that kind of stuff. And at some point in time, we decided to move towards the public viewing sessions that we host out at the Sugar Grove Nature Center. And we'll still do that this year. But with last year's cancellation of everything, we just didn't really have this time to just sit and gab like we used to, and so we thought we would initiate this online thing this year, and see if we could kind of get back to having member, kind of meetings. And obviously, not everybody here is a member of Twin City Amateur Astronomers, and you're welcome, and we're glad to have you, and we're thrilled that this the technology that has kind of emerged out of this whole COVID mess is enabling more of these kind of interactions. And so here we are. This is the first of our monthly series that's currently scheduled to go through December, and we'll evaluate after all of that and just see how the uptake was, and if we want to continue doing this. But tonight we have our friend Dr. Sunil Chibolu, doctor as in doctor of mathematics. Um, and he's going to go all infinite series on us here tonight.
Oh, no, 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 no.
Um,
No sophisticated math today. It's going to be nice and easy.
And talk to us. And Sunil is a member of our board, we've already as a club learned an awful lot from him about how things work in astronomy, and he's very much into the math of astronomy and those kind of things. So tonight he's going to talk to us about time, and time, of course, is fundamental to astronomy. Without the ability to keep time and tell time and predict time and all that kind of stuff, we kind of don't have astronomy. So he's right down in the grassroots of what astronomy is all about. So without further ado, I give you Sunil Chibolu.
All right, so thank you very much for that great introduction, Tim. So thank you all for coming. Good to see some familiar faces and some new faces too. So I hope you will enjoy this presentation. So I'm here to tell you a brief history of time. So let me share my screen and get started. So hope you guys can see this, right? So let me go to my view options and make sure I can have everything here. All right.
You can see it.
All right, good. So the talk is about time reckoning, astronomical calendars, and clock. So before I get started here, a few acknowledgements. So I would like to thank, first off, TCAA for giving me this opportunity to present. I know there's lots of people here who are more knowledgeable on this topic than I am. So I really appreciate having this opportunity to present this. So thank you. I also want to thank Carl Benning, among other members. So Carl gave me some nice pointers for this presentation. I appreciate that. And some of these topics were initiated when I had some interesting conversations with a former graduate student, Lisa Zeiger, and she's somewhere in the audience, I hope. So I want to thank her for that. And so we both were planning to write a paper on time and some topics related to time and mathematics. And last but not the least, I want to thank my daughter Shloka Chibolu for helping me put together some of the slides. Now with all this online classes, these kids know more about computers than I do. So, all right, so let's get started. So before I tell you what I'm going to speak, I should tell you what I'm not going to tell you. So I'm not going to tell you what is time. So that's a very, very deep concept. one of the most abstract and intriguing concepts of the human mind. So there are very deep questions which are of very fundamental nature, and I just throw some here. So these are not the questions I'm going to cover in this presentation, but I want to put them out here because I think these are very interesting, very important questions nevertheless. Some of the best minds in the world, great philosophers, have given these questions some serious consideration. So is time real, or is it just an illusion of the human mind? So when did it start? When will it ever end? Maybe these questions even don't make sense. Is it discrete or continuous? Does time have a direction? I mean, there are some cultures where time is regarded as a cyclical thing, And does time have more dimensions? All right, so these are deep questions. But I will say that in classical physics, time is something that's absolute, and Einstein said time is relative. But I will leave you with this interesting aphorisms. It's one of the most hilarious one. It says that time was invented by clock companies to sell more clocks, by Karl Marx, who's one of the great philosophers. So, okay, these are not what I'm going to address. So what am I going to address? So for this talk, I have a different set of goals. We're going to focus on more tangible questions. How do we measure time? So my previous talk in TCAA was about measuring distances. Now we're going to talk about measuring time. How can we read the time from the sun and from the night sky? Our wristwatches, those are relatively very recent inventions. So only after the age of exploration, so in the last 200, 300 years. But how did astronomers and people read the time? And then being a mathematician, I'm drawn to questions of why do we have 24 hours in a day? Why do we have 60 minutes in an hour? Some very simple questions, basic questions. Why do you have 7 days in a week and so on? Now, are these random numbers? I mean, surely not. It turns out the story of astronomical clocks has a very interesting mathematical structure. And among other things, that is something I would like to showcase tonight for you. So, and then about calendars. Why do we have leap year once every 4 years, but not every 100 years? Is the calendar that we are having, is it perfect or can we improve? So these are among the questions I would like to consider. So time is a physical quantity. As we all know, to measure any physical quantity, you need, you need a unit. And time is no exception, right? So what is the most natural unit of time? Well, whatever it is, it should be based on something that's periodic and measurable in nature. So of all periodic things that are happening in the cosmos, what is the one which has the most profound impact on our lives? Well, that is clearly the rising and setting of the sun. Human beings have been seeing this since the dawn of civilization, ever since they have evolved on this planet. The ball of fire rising in the east and setting in the west. So what can be more natural than the length of a day? So clearly that should be a fundamental unit. But once you have a fundamental unit, you immediately have derived units coming from that. Well, take multiples of the fundamental unit, that will give you weeks, months, and years. Take fractions of the fundamental unit, that will give you hours, minutes, and seconds. So in a nutshell, number one leads to the problem of calendars. Number two leads to the problem of clocks. So once again, starting from the fundamental units, you want larger units, take multiples. You want smaller units, take fractions. Well, I will say more about these problems of calendars and clocks later. So, but the calendar problem has to deal with the length of the year not going evenly into the length of the year is not a multiple of the length of the day. And then for clocks, it is about designing perfect timekeeping devices. All right, so the key is to get the length of a day. That is the fundamental unit. All right, so how long is a day? So if you ask a common man on the street, they'll say 24 hours. That's how long is a day. But the question is, has that always been the case? Here's a surprising fact in case you did not know this. During most of Earth's history, the day was actually much, much, much shorter. Well, so when the Earth in its infancy, when there was no moon, it was about 6 hours, according to some theories, or most theories, it's about 6 hours. And then when the Earth was a toddler, it was about 8 hours. So the length of day was actually pretty short, about 1/4 or 1/3 of what we are used to. Okay, and then the moon was much, much closer to the Earth as a result, and then it was actually huge in the night sky. And some historians say that at that scale, I mean, there were no people, there was no life back then, but there was anybody there, they could count possibly the craters on the moon with naked eye. So it was that big. But then over time, the Earth is aging and it's slowing down, but it's still obeying the law of conservation of angular momentum. So often when people talk about day and night, they talk about the sun and the Earth. But what determines the length is moon. That has a lot to say because of the tidal friction. The Earth is slowing down and then the moon is receding away from us. So the length of the day is getting bigger. All right, so let's take a closer look at the definition of a day. What is a day? Well, the textbook definition would be something like this: the amount of time the Earth takes to make one complete rotation on its axis. That is what a day is. Well, that is a nifty definition, but it's useless because how are you going to tell whether you've completed one complete rotation or not? Because the universe does not come with a fixed set of coordinates to measure it. So the best we can do right now is to look at stars which are extremely, extremely far away. But here is perhaps a working definition. So the amount of time lapsed between the sun reaching its highest point in the sky on 2 consecutive days, like from sunrise to sunrise. Okay, so 1 is a working definition, is a theoretical definition. 2 is a working definition. So natural question, are these 2 the same? And the answer is no. 1 defines what we call the sidereal day, and 2 defines what we call an apparent solar day. So what's the difference? As I tell my students, a picture is worth 1,000 definitions. So you look at Earth here as it's going around the sun in its orbit with respect to a certain distant star. At this point, it has completed 1 rotation. But because the orbit has a curvature, it has moved along in its path, so it has to spin a little bit more to bring the sun back to the same position. So you can do a little bit of math to figure this out. So we teach that in geometry. You have parallel lines, and this is a transversal. So these 2 angles are congruent. So how much is this angle? Well, 360 degrees it spins in 24 hours. So in 1 degree, in how many hours? Well, that has to be the fraction 24 out of 360. Well, multiply by 60, you get 4 minutes. All right, so which means the sidereal day is about 4 minutes shorter than the apparent solar day. A very important fact for all astronomers because it has the following striking conclusion. That is, any star rises and sets about 4 minutes earlier each day. Okay, so let's see this one. I'm going to open Stellarium here. I'm going to stop share and I'm going to do a reshare so that you can see the effect. So here is the desktop version of Stellarium. So if I tell you that Vega rises at 7:20 today, so you should know that tomorrow it will rise at 7:16. So let's take some star here, Arcturus. So on the left here, you can see there's a lot of information here, but the rise time is 2015. So now what happens if I advance the clock? So it's 2011. It's too small, but you can see here, it's 27. So every time I advance the clock, so the rise time is getting shorter. And you look at the sky, the stars seem to be shifting position 1 degree in the counterclockwise direction. Well, that is because we are using our civil time and not the sidereal clock. So in astronomy, people use sidereal clock. All right, so that is the difference. So we've seen this. But clearly the apparent solar day was more important for people because that's the one which has more impact. So the Egyptians were the first people to actually divide the day into smaller units of 24 parts as we know today. And so they said 12 parts of daylight, sunrise to sunset, and 12 parts of night marked by passing of 12 constellations. Now, the important fact to remember is that for most of humankind, these parts were not equal. They change with season, because in the summertime, there would be, the hours would be longer, in the wintertime, they would be shorter. But that didn't disturb them. That's how the things carried on, you know. But why 12? Why not some other number? And you also see this in Indian calendars. There's something called Tithi. It's the time taken for the angular separation between the sun and moon to increase 12 degrees. So this 12 seems to be coming up in a lot of civilizations. So I asked myself, why is this so important? Well, believe it or not, the answer to this is rooted in evolution. So many ancient civilizations had this habit of counting on knuckles, and it so happens that we humans evolved with 12 knuckles on 4 fingers, and that perhaps has some evolutionary advantage. And the thumb being the smaller one, people could count easily. And once they complete 10, so that's a dozen, and you close one finger and count another 12, that's another dozen, count another finger. So 12 times 5 is 60. And that takes us to the Babylonians, who worked in the sexagesimal base system, which is base 60. So among all ancient civilizations, so this is the civilization which had the most sophisticated base, because the advantage of working in a base which has a lot of factors was well known to Babylonians. So those are the factors of 60. And there is no other number less than 100 with more factors. Well, if you don't believe me, you can go and check. And the number 96 also has 12 factors. But anyway, they use base 60, and we see that in our modern lives. You see, our division of an hour into 60 minutes and a minute into 60 seconds can be traced back to the ancient Babylonians. So that is how the division started. So 12 knuckles, and then this base 60 that gave the splitting of the day. But now, how do we measure this? So people started using sundials to measure time. And I mean, there's a long history of sundials, but I'm going to put here this sundial. I'm personally attached to this because I was in Beijing. So this is in the Forbidden City in Beijing. So that's an equatorial sundial. So meaning this gnomon, this vertical stick, is parallel to the axis of the Earth's rotation. And because 15 times 24 is 360, so roughly that shadow will sweep 15 degrees every hour. So that will help people identify the passing of time. So my daughter and I, we made a model of this one in our backyard using swim rings. So that is a replication of this equatorial sundial. So here in Bloomington, so this will be at 40 degrees to the horizon. And then you have markings on this ring, which will read the time from the shadow. So there are several other historical sites worldwide. So there's one famous one, which is called Jantar Mantar. It's in Jaipur, India. Carl Benning has been to this one. So this is one of the world's largest sundial. It's called Samrat Yantra. Samrat is king, Yantra is machine. It's the world's biggest sundial. And it is so precise that it can actually read down time to seconds, you know. It's quite a fascinating site here. And they have many of these, I think something like 18 or so. I didn't visit this one, but I had the pleasure of seeing the one in New Delhi. So this is Jantar Mantar. I was there in the year 2000, shortly before coming to the US. Anyway, so these are sundials which tell us the time. But then there's a problem. Even though they're giving the apparent solar time, you know, the solar day is apparently not constant. And why is this not constant? It turns out that there are two troublemakers. One is eccentricity of Earth's orbit, and the other one is obliquity. What is eccentricity? As we know, the Earth in its orbit around the sun is not perfectly circular. It's a conic section. It's an ellipse with sun at one foci. So, and then when it spins, it makes an angle of about 23 degrees, which is important for explaining lots of things, including seasons and so forth. Anyway, so as a result of these two troublemakers, the length of the day is not constant over the course of the year. And that leads to what is called the equation of time. So the graph here on the left shows you the length of the day and how it varies over 365 days. So in January and February, it's running more than average. The length of the day is more than average. And in March through May, it's below average, and so on. So it kind of fluctuates. And what is this y-axis? This is measured in seconds. As you can see, the variation is somewhere between 30 seconds and 25 seconds. So plus or minus, let's say 30 seconds. That is the variation of the length of a day. Now, on the right here, we have the compounding effect, because all these long days and short days, they can occur in succession, and that can add up. So mathematically speaking, the curve on the right-hand side is the integral of the curve on the left-hand side, and the curve on the left is the derivative of the curve on the right-hand side. So this shows when the watch is faster and when it's slower compared to the apparent time. So the watch, the time in our wristwatches is some kind of an averaged, a standardized version of what we see in the night sky. So it's seen the solar clock. So that is the equation of time. So note in particular that only 4 times during the year, the mean and apparent solar times are equal. That corresponds to the points where this graph crosses the x-axis, which is corresponding to the 0 line. Here, here, and those 2 points. And September 18th is going to be your shortest day, and December 22nd is going to be your longest day in the year. So as you can see, December 22nd, it shoots up here. So it's 30 seconds more than average, and September 18th is about 22 seconds less than the average. Not to confuse with daylight. So different parts of the Earth will have different daylight, but all parts will have the longest day on December 22nd and shortest day is the September 18th. So therefore, the point is that there needs to be a correction. So if you look at some of the more recent, later sundials, so these are called, I mean, you can get one for your backyard. These are the garden sundials. So you have the sundial, and here down below, you see the equation of time. So which means you get your reading from the sundial, and then you look into the graph here, and you will know what the correction is, how much you should add or subtract from the date. So that is how time was measured for a long time, until human beings felt the need for some devices which don't have to depend on the sun. Because for one thing, sundials apparently didn't work well at nighttime or when it's cloudy. So there is a long history of evolution of clocks, and that will be a topic of another talk later in the year, but I'll just put up here water clocks, starting from Greek civilization, so which were calibrated so that the markings of the water level correspond to the markings on the sundial, so that they can use during nighttime. And then, a lot of the ancient civilizations actually flourished in mid-latitudes where water never froze, even during wintertime. But there was need for other places. And then there are parts of Europe, starting in the 16th century, Galileo, Christian Huygens, they came up with pendulum, where one swing corresponds to 1 second. And then more precise timekeeping instruments, which will be robust, which will not be affected by temperature and humidity in voyages at sea. That led to more sophisticated missions. And this one is John Harrison's piece, the man who actually solved the longitude problem, culminating in the more recent quartz clocks.
It's a great book, by the way.
Okay, the transition here is from temporary to canonical hours. I think that is important. As I said, for a long, long time, human beings were just using temporary hours, which are not uniform over the seasons, right? And this evolution shows the transition. Somehow time was liberated from its traditional classical roots embedded in Earth's rotation to something more independent, which depends more on mechanics of springs and pendulums and other things. Okay, reading time from the moon. So here's a question for you guys. So if you go out in the night sky to do stargazing and then you see the moon, so the question is, can you look at the moon and tell approximately what time it is? The answer is yes, you can, if you're very careful in the computation. So let me show you how this is done. For this, you need to know the moon rise and moon set time of each phase of the moon. That's not too bad, I'll show you how. And the moon is up for 12 hours in the night sky. And then if you know the rise and set, you can do a clever interpolation to find the time at any other point. So my Math 260 students will understand this. 3 and mod 12, we're talking about modular arithmetic. So here are the principal phases of the moon. In the second column, I have the rise time, and in the last column, I have the set time. Every astronomer would know this one, the first row, very well, because they love the new moon, because it rises at 6 a.m. and it does all its business by 6 p.m. and astronomers can go out and do their stargazing, right? And then you add multiples of 3, 6, 9, 12, 15, modulo 12 is 3, and so on and so forth, right? And you change the AM to PM and PM to AM to get the rise and set time. So it has a click. So here's the situation. So now if you know this table, now it's quiz time. So here is moon. We are up in the northern hemisphere, and you see the moon is at its highest point and passing through the local meridian. Question, what is the local time? So anybody wants to give it a try? Yeah, so first off, yeah. So the moon is up in the sky and the left part is illuminated. That tells me it is waning, which means it is in its third quarter. So if it's in the third quarter, okay, or last quarter phase, so it rises at 12 a.m. and sets at 12 p.m. So which means this should be halfway between the two things. So that means this should be approximately 6 p.m. And there it is. Well, there's going to be an error. I said it can't be very precise, but 6:23, that's the true time. So next time when you go out in the night sky, see the night sky, the moon, take this as an exercise for yourself. Try to guess the local time by looking at the position and the phase of the moon. This also explains this famous question, why do you have 7 days in a week? I recently wrote a paper on this, and just last week I heard back from the editors. So they said they're going to publish it, they like it. So what is this? In this paper, I explained why we have 7 days in a week from a mathematical standpoint. The story again goes back to the ancient Babylonians who rounded the synodic month of the phases of the moon to 28 days. Well, that's kind of strange because the lunar month is 29.5 days. So any reasonable rounding should be 29 or 30, but why did they do 28? Well, you know one thing, these Babylonians, they knew the importance of having factors, and 29 happens to be a prime number. So 29 is no good. But then they didn't do 30 either because there was no factorization of 30 which had any astronomical significance. But 28 had one. So 28 is 7 times 4. And each principal phase of the moon lasts for 7 days. And hence we have a 7-day week. But then of course they had to add extra days to do this correction of leap days in the month. So that is the story of 7 days. But then you can also tell time from the stars. When you look at the night sky, there is a beautiful clock, imaginary clock in the night sky. So the Big Dipper, in the course of the day, it does this cartwheel motion around Polaris. Polaris is a star that's stationary, doesn't move relative to other stars. But the Big Dipper, if you look at the 2 pointer stars pointing to the North Star, as the Earth moves in the clockwise direction, the celestial sphere has a counterclockwise direction. Unlike the ordinary clock, this one has 24 hours. The wall clock we are used to has 12 hours, and this one has 24 hours. It spins counterclockwise, not clockwise. And the hour's hand connects the Polaris and the 2 pointer stars in the Big Dipper. One great thing about this clock is that it agrees with the civil time or mean solar time one day of the year, and that is March the 8th. So it so happens that on this day, if you just look at this clock, that will be what's the time on your wristwatch. But then I mentioned earlier, this clock, this is the sidereal clock, which is gaining 4 minutes every day. So for other days, you do a simple correction. So get the time, and then you subtract 4 minutes times the number of days passed since March 8th. And that will give you the time. So here is another exercise for you. If you're going out stargazing, just look at Polaris and Big Dipper and use this information to figure out the time. So 2 homework activities for my students. Tell the time from the moon and its phases, and then tell the time from Polaris and the Big Dipper time. So as you can see, in order to tell time, you can rely on stars and the moon. So here I just want to show you this motion. I got it from Sky Safari Pro. As you can see, this is Polaris, and then there is a cartwheel motion here of the Big Dipper over the course of the day, and that is what we are going to use to tell the time. Okay, so all right, so that is the story of clocks. Now change to calendars. How am I doing on time? All right, calendars. There are so many calendars in the world, and you can roughly group them into 3 main categories. One is the solar calendars, which rely on the sun, and the lunar calendars, which rely on the moon and its phases, and the lunisolar calendars, which take into account both the moon as well as the sun. So here are some examples. Our Gregorian calendar that we use is a solar calendar. The Islamic one is a lunar calendar, and India and China, we use the lunisolar calendar. The Panchang is the Hindu calendar. Okay, so but no matter what calendar you use, you're confronted with some problems, which I call the calendar problems. To explain these calendar problems, I'm going to introduce these 3 variables: D for day, M for month, Y for year. So let D be the length of the mean solar day, M be the length of the lunar synodic month based on the phases of the moon, and Y the length of the tropical year. All right, so here on planet Earth, we have this inequality, D less than M less than Y. There are other planets, even within our solar system, where the inequality can be other way around. So I think for Venus, the length of the year is smaller than the length of the day. But we are concerned about Earth, so we have this inequality. And this, I believe, is the most succinct way of presenting all calendar problems, divisibility problems. None of these numbers divide evenly into other. So 3 problems. The problem of the solar calendar is the length of the day does not divide evenly into the length of the year. Problem of the lunar calendar, the length of the day does not divide evenly into the length of the month. Lunisolar calendar problem, the length of the day does not divide evenly into the month or the year. Okay, then you might say, well, who cares? You're a mathematician, so you're working with numbers, you care about divisibility. But the answer is no. This is going to be very important, because if you don't address these issues, you have a serious problem called the calendar drift. So calendars can become ahead or behind seasons, and that's problematic. So days and months have to be adjusted to account for calendar drift. And this happens in every culture, every calendar. So in the Gregorian calendar, we have what is called leap days. You have to insert leap days every so often to bring things back in alignment. And in the Hindu calendar, we have something called Adhika Masa. So you add an extra month, because it's mostly a lunar-based calendar. There'll be 12 cycles of the moon, but then that's 350 something, and there are 360 something days. So, and this is going to add up. So every 2 to 3 years, there's an Adhika Masa. But then you can't just keep adding adhika mas, adhika mas. Adhika is extra month, right? But that's going to pile up. And then you have to subtract months. Kshaya, so that is deleting months. So you have to constantly keep doing this addition, deletion, to keep things on track. So I'm going to define something called drift index. Okay, this is something I just made up. There is nothing in the literature called drift index. For the purpose of this talk, what is a drift index? For any calendar, drift index is the number of years it takes for the calendar to drift one day. So clearly, higher the drift index, better is your calendar. So let's look at some examples then. So here is the precise value of 1 year, 365 days, 5 hours, 48 minutes, 45 seconds, and 138 milliseconds long. So if you turn that as a fraction of days, it's 365.2421891 days, to be very precise. Well, if you say, I don't care about the fractional part, I'm just going to be happy with 365 days, fine. What's going to happen then? Well, the season is 0.24 longer than your calendar. So every 4 years, there is a drift of 1 day. So the drift index of this calendar is 4 years. And this is what people live for a very, very, very long time. And as you can see, that looks not too bad, but every 28 years, summer will be starting a week later. And that would be not good. So then in 46 BCE, Julius Caesar said, I'm going to fix this problem. So he said, we're going to add an extra day every 4 years. So then the year is 300, actually that's a typo, 365.25 days. Well, that's a pretty good rounding to the first decimal place. So 365 plus a quarter. But then you shoot it a little bit more. You want a 240, make 25. The drift index of this is 128 years. Well, that's more than a century. Who would notice, huh? But then by 16th century, people started noticing that seasons were off by 10 days. And the Catholic Church was upset because there are some religious holidays which have to happen at certain times, right? Easter has to be on the first Sunday following the first full moon, following the first the equinox. I mean, there are some restrictions when these religious holidays have to happen. So time to fix that. So that led to our modern calendar. 1582, Pope Gregory the 13th. So figured that we have 3 more leap days every 400 years. So how are we going to fix this one? So he hired some mathematicians to fix the problem. So they came up with the rule that we all learn in school. So if the year is a multiple of 4, leap year. But unless it's a multiple of 100, it's not a leap year. But if it's a multiple of 400, then it's a leap year. So the effect of this is that it cuts down 3 more leap days every 400 years. So 1 year is now, in this model, 365.2425, which gives you this rational approximation. And this is what Carl sent me. Thank you, Carl. So how good is this one? The drift index for this one is 3,216 years. That's pretty good, yeah? And this is so good that it is the one we still use today. Okay, so now the next question is, did everybody get on board? No. It's not easy to convince all countries to get on board. So in 1752, this was started in the 16th century, and then this is into the 18th century. So United States decided to get on board in 1752. And you look at these calendars, you see something really odd here. Look at the month of September in the United States, 1752. Well, you have Tuesday the 1st, Wednesday the 2nd, and then they had to jump to Thursday the 14th. Because by that time the seasons were already off by 11 days, so they had to drop 11 days in the calendar. So September 2nd followed by September 14th in 1752. Yeah, so it was a huge mess when every country was having their own calendar until things got standardized in 1752. Question, can we improve this further? And the answer is yes. You can keep on adjusting in this manner for millennium years, and then the drift index becomes 68,000. well, all this is good, but that is getting overly complicated. It reminds me of a bag which has a lot of holes and I'm using duct tape to fix it. Okay, there is on one hole, I'm going to fix it. So why don't we just throw this bag and get a new one, right? So can we do better? And the answer is yes, a lot better. So just go back to the Julian calendar and fix it. So remember, the Julian calendar drifts 1 day every 128 days. But actually, if you look at the exact value, it's pretty close to 128. It's 128.026. So why don't we just skip 1 day every 128 years instead of 100 years? So if you do that, the drift so this is going to be the new rational approximation for the length of the day. And as you can see, it agrees to the 1, 2, 3, 4, 5 decimal places. Brilliant. And the drift index is more than 500,000, 625,000 years, right? But if you do one more thing, guys, that's it. If you take out one leap day every 625,000 years, guess how good this calendar is? So this calendar is good for eternity. So the drift index is 10 to the power of 13, which is more than the life expectancy of the sun. You can't do better than that. So, but then you might ask, okay, why did people not get on board with this rule? They said, oh my God, how are we going to remember 128? We're going to forget it. So better be 100. Well, this is the human obsession with base 10, But then mathematicians offered the solution that express years in binary to remember this rule. So just by accident, it happens that 4 is a power of 2 and 128 is also a power of 2. So from now on, we're going to propose this new rule: express the years in binary. If the last 2 digits are 0, leap year. Unless the last 7 digits are 0, it's not a leap year. That will fix the problem for more than 1,000,000 years. So here are some examples. 2020 in binary ends in a 00, it's a leap year. 01, not a leap year. 10, not a leap year. 11, not a leap year. 00, back to leap year. So it cycles in groups of 4 unless you come across a year which has a string of 7 zeros. Then it's not a leap year. So these are multiples of 128. So I think this is a better calendar system than the one that we currently have because it's more cleaner. All right, that's where matter stood for a long time. And then a big turning point in 1967, which led to the inception of atomic clocks with the development of new ideas in particle physics and atomic physics. So before 1967, a day was divided into 86,400 equal parts because there are 24 hours, 60 minutes in each hour, 60 seconds. So that is the definition of a second. But then in starting 1967, the following strange definition took its place. A second is the time it takes a cesium-133 atom at ground state to oscillate 9,192,631,770 times. Well, that looks like a random number, but it has been very carefully calibrated so that it lines up with a second. But the beauty of this one, it takes more than 1 billion years for these clocks to gain or lose just even 1 second. Okay, remarkably precise. In fact, there is this high precision instrument at the what is that called? American Institute for Standards or something, where they say that these clocks, if they have been running since the time of Big Bang, so maybe they'll just lose a couple of seconds at most. So this is the basis of the International Atomic Time for GPS, for satellites, high precision experiments at CERN laboratories and so on. But then now your standard is changed. It's no longer Earth, it's the cesium atom. So the fundamental unit is not coming from Earth anymore, it's coming from this cesium atom. So, but then we still can't disregard Earth's motion. There will be fluctuations and irregularities in the motion of the Earth. So then we have to add leap seconds. the International Earth Rotation and Reference System Service, they compensate the irregularities by adding leap seconds every 21 months on average, right? And typically these are inserted just before midnight on New Year's Eve, right? So when the big ball on Times Square, New York drops on New Year's Eve, you may not notice in some years, the countdown begins, and then you will have this time, 23:59:60, because they just inserted a leap second. And Carl told me that the person who's in charge of adding this leap second is his friend, so he can tell us more about that. All right, guys, so that's my concise story of time starting from sundials to atomic clocks. And these are my references. And thank you for your attention.
Thank you, Sunil. That was very cool. Some of the stuff that you put in there is new to me. So I don't know if you know this or not, but you can actually buy an atomic clock. If you got $1,000 or so, you can plunk it down. You can have your own atomic clock, and it's based on cesium. So, you know, I think the club needs its own atomic clock. Do I hear a motion?
I make a motion for buying one.
I know that there was one question that appeared in chat. Somebody asked about Planck time. And this is getting down into the quantum and is it discrete or continuous and all that kind of stuff. So
yeah, so Planck time. So I'm a mathematician. I will defer that to more physicsy people in the audience. Maybe Carl has something to say about Planck's time.
I don't know if Carl has anything to say about Planck time. I think it's a pirate thing. I think you walk the Planck time. Carl.
I was just typing a message. No, I've got nothing to say.
You're not a Planck time kind of guy?
What?
So you're not a Planck time kind of guy?
Oh yeah, I know what Planck time is. 10 to
Yeah,
minus.
that was a question. Can you give us a quickie on Planck time?
Well, there's not much to say as far as I'm concerned relative to what we're talking about here, because it's just, to me, I don't see it as being a germane aspect of this talk. So
well, it was a question that came in the chat, Carl. Somebody asked about it in the chat.
Okay, so you know it's roughly 10 to minus 34 seconds, and it basically turns out to be the point in time past which we cannot work out the solutions to the nature of the universe. It is the absolute earliest we can go in time. That's the simple way of looking at it.
Okay, all right. So that kind of addresses that question.
Any other questions?
Yes.
No other questions?
I had a quick, two quick questions actually.
Hi, Michael. So Michael is my student. Yeah, tell me, Michael.
So one of my questions was when you were talking about the ancient Egyptians and their split of like the 24 hours into the 12-hour chunks of like sunrise to sunset and then like the stars, then why don't we start like 1 a.m. at sunrise? Like why does 1 a.m. fall as to where it is if those are like the two divisions of 12?
Yeah, so these are very difficult questions because the history of time is so convoluted and long. There are so many historical oddities in this story. I know there have been several changes and several countries, different countries were using on different scales. And I think this standardization actually started, I won't say in the 18th century. Prior to that, everybody had their own time. There were no proper time zones even, you know. All this time started when I think the railway industry started going, you know, people had to have uniform time. So that's when time zones and clocks and everything came about, you know. So, well, it's not clearly answering your question, but I think somewhere around there, people figured out this is the way to do it. And not all decisions were based on logic. Some of them seem to be somewhat ad hoc, you know. So, you know, we do live with these historical oddities in the story of time telling. And also, by the way, the link to my talks are on this page. So if you have a phone, you can use your QR reader, or you can just directly go to that and you can access the slides.
I have a question.
Yes.
So you were saying that the Babylonians, I don't know, they found out, you were saying like the number 7.
Uh-huh.
You were mentioning that. But didn't the Babylonians use like a 360-day calendar? So wouldn't that be different?
Well, so the Babylonians, it's not about the calendar, but I'm telling the base 60 that we use for time division of hours into minutes and minutes into second, that actually traces back to the Babylonians, because the Babylonians used the sexagesimal base system. They were working in base 60. It's not that the calendar has 60 days, they're working with base 60. That was their operational base.
You were like mentioning that they like 29.5 days in a month, and they rounded it to 28. That's what I meant, but like they use like a shorter calendar.
Yes, their month, the lunar month, they rounded it to 28 days, which then led to a 7-day week.
I don't remember. In fact, this was something that I learned in David McDowell's history of Western civilization class, or ancient Middle East. I don't remember, Sharon, which one it was, but there was one culture whose year was 360 days. And at the end, they had a 5 or a 6 day like drunken brawl that no one could remember anyway, right?
Right. So, and yeah, I was reading, this is, by the way, this is a very good book. I recommend for people who want to know the story of time. It's Time's Pendulum. It's in the references. It's by Joe Allen Burnett. So the quest to capture time from sundials to atomic clocks. It's a fantastic read. I recommend people who want to know more about time to read that book. Yeah, and these things, I mean, the one called, Tim, you're mentioning, so even the week, I think the Romans had like, 8-day week, and there are some other countries which had like 10-day week. It was like a huge mess for a time until everything started standardizing.
The whole thing of time zones was, if you use solar time, then it's never the same time anywhere, right? So Peoria has a different time than Bloomington does, and you can't actually. And so when the trains started crossing the large expanses, there was no way to really tell when the train was going to get there or not, because the times are always different, So.
Yeah, that's right. Yeah.
But I object strongly to daylight saving time versus standard time. There's zero astronomical reason for that. There's zero societal reason, but there's all kinds of reasons that's a bad idea. So I'm on the record as that. If I ever run for president of the United States, one of my campaign promises will be to get rid of daylight savings time.
Yeah, I think time is a very fascinating topic, because we thought we understood time, and as late as the 20th century, Albert Einstein proposed his new ideas, which has completely shaken our foundation of time. And who knows, maybe there are more breakthroughs to come, and we will learn more about the fundamental nature of time.
Yeah, when you started out asking, what's the definition of what's the best unit of time, I was going to say miles. But I held my tongue.
Yeah, so there is so much of activity in the chat. I was not paying attention to that because I was talking. I'm just seeing if there are any other questions.
Well, the chat is just I've been watching it. People are saying thank you for the great talk as they drop off mostly. But it sounded like you had read Longitude, the book. Yeah,
yes.
That's another great book about time. And And
Yes, the story of longitude. Yes.
yeah, the deal there is that the British Admiralty was tired of losing fleets because they didn't know where they were,
Exactly.
right? And so
Exactly.
they sponsored a contest for the person who could successfully solve the problem of determining what longitude you were at. They could easily tell what latitude they were at,
That's right.
but not longitude, you know?
Yeah, so that is something I plan to talk later this year. And that problem of longitude is actually boils down to a problem in engineering because what has to be done was clear, but how are you going to do it? So it came down to building clocks which will not lose or gain time when traveling at sea. Because pendulums, as we know, as the temperature increases, the length will increase, and then the amplitude, everything will going to change. But yeah, so
with the ship rolling and everything, the clock couldn't keep good time. Yeah,
that's right. That's right. Yeah.
they tried it with sand. What do they call those? Sand clocks, you know, but
Hourglasses.
it wasn't good enough. Yeah, hourglasses, but it wasn't good enough. You know.
Yeah, but I think there was some very interesting ideas even by Galileo. He was using the moons of the Jupiter to tell the time, because those days people had telescopes. They didn't have watches, ironically. So they
Right.
so they could see the moons of the Jupiter, and looking at the Galilean moons, he made a table to solve the longitude problem. And then there is the lunar distance method. You know, there's some very interesting methods in time telling the time at sea. You know. So yeah.
Yeah, even lunar occultations, they would predict when the moon would occult certain stars, and you could tell what time it was in more or less absolute terms by watching the occultation and knowing when it was predicted. So there was
Unless it was cloudy. Unless it was cloudy.
Yeah, unless it was cloudy, exactly. All of those techniques had real problems. But even when Harrison finally invented the chronometer, the captain had to remember to wind it. And if the captain forgot to wind the chronometer, that was like a disaster. He was going to lose his command of, he's going to lose his commission for over that, something like that. You know, that was a court-martialable offense.
Then the issue became one of an administrative agency and whether they were going to give him credit.
Right. Yeah. Yeah. He did collect on the reward, but he had to go like to the Supreme Court of the English, blah 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 blah, and it was, he was a very old man by the time he actually collected the winnings for that.
And then he only got part of it.
Yeah. It's here. So I don't know if you know this, Sunil. There was a museum up in Rockford called the Time Museum.
Oh no, I did not know that.
It had Harrison's H4 clock. I think it had one of his earlier clocks. There was all kinds of timepieces up there in that museum, and it went bust, and that whole collection was dispersed to private owners. So
I see. Yeah. So actually, Carl told me that he knows the person who's in charge of adding the leap seconds. I was very intrigued. So, that's very
Boy,
cool.
Can you imagine hold you hold your finger on the button for too long and you just added 2 seconds?
Yeah.
Sunil, I had a question, I guess.
Yeah, sure, Venkat. Yes.
Hey, you mentioned obliquity and eccentricity in your talk. They're really interesting to see how complex Earth's rotation is and revolution.
Oh,
so,
yeah. So
my question was, is the atomic clock looking into those changes, and is it making it a lot more accurate with how we track?
Oh yeah, right. That's right. Because you see, the equation of time graph that I gave you, it's actually superimposition of two sine curves. So one coming from the eccentricity of the orbit, the other one coming from the obliquity. So that's why it doesn't look like a sine curve, but actually like a combination of two sine curves. It looks like this funny curve. But then the atomic clock business, yes, and that is the reason why you're getting those leap seconds, because they have to calibrate the very fine changes in the Earth's motion, tidal forces, whatever. Yeah, and that is why you have this correction every few years.
From what I understand, the eccentricity and obliquity, I was reading some NASA article recently. they last about, no, they have a cycle, but they last about in thousands of years, like
Oh, yes,
41,000.
yes,
Some of
right,
them is
absolutely.
100,000.
Right, right. And in fact, the apps that you use, Sky Safari Pro and the Stellarium and all these apps, even they have to update the coordinates to take into account every few years because of the precision of the equinoxes and all this very fine details, you know.
Okay, thanks.
Yes, yes.
I'm not yet a geomagnetism expert, although I'm working on it. But as I understand it, the atomic clocks are used even to measure changes in the Earth's rotational velocity because of the rising and falling of convective magma masses in the interior and stuff like that.
Yeah, so now I think we know the motion of the moon and Earth very, very precisely because, you know, these NASA astronauts, when they walked on the moon, they left behind several things. And one of the things they left is retroreflectors on the moon. So they can actually bounce radio waves and get the signal back. They know exactly the position, the time, down to a fraction of a second, you know. So I was going to mention that in one of the slides, but I did not, you know. So
I'll mention there's a good time museum up in Elgin. It's not surprising since Elgin Watch was up there for so many years, but it's a museum worth visiting if you're interested in timepieces and that sort of thing. And as far as references go, actually, many of us here might have a copy of the Royal Astronomical Society of Canada's Observer. That has a good section in it on time. It looks at things like dynamical time and the various aspects of time that play an important role in observational astronomy.
Mm-hmm. Okay. Yeah, thank you. Yeah, there it is, Observer's Handbook. I have a copy of mine too, somewhere here.
This is last year's. But,
Well, anything else anybody would like to chat about, or any more questions for Sunil?
I put a question in the chat. I'm not sure if anyone saw.
Okay, so I'm scrolling down through the chat.
Yeah, there's an idea I read that theorizes an apple falling across space-time down the continuum. With that being said, could we, in theory, reverse this effect? I've heard that this may be possible from colliding black holes, in which you could hypothetically take a certain path throughout them that would land you in the past.
This is way beyond my expertise. So my friend Anindya Sen, if he was here, he would be the right person to answer this question. But I'm sorry, that is outside my territory. But I have to do some research and get back to you on that.
So, Sunil, you know, this is one of the questions on your first slide. That basically, you know, is time a one directional thing, or can it reverse direction? Or if it did, how would we even know that it did? And I mean, weird stuff like that, right?
Yeah. So, I mean, some of these questions are even hard to formulate. So what do we mean by reversing time? And what does it have multiple dimensions? You know, so it gets very deep and philosophical, some of these concepts.
Yeah.
So we can leave that to the Twin City amateur philosophers, I guess.
Well, or Brian Greene has his PBS series and his books, of course, delve into those things. And like that idea of threading your way between two colliding black holes and going back in time, that is an idea that's currently kicking around, you know, in the highly theoretical end of astrophysics right now. Also, you know, another good source of that looks at some of those kind of questions. If you go on YouTube on the PBS Space Time channel, they address some of these kind of things. They actually have a series of fairly lengthy and highly detailed videos that delve into these topics. You have to sometimes solve differential equations to work their puzzles at the end of the videos, for instance. So, you know, nonlinear differential equations and all else.
Sunil, do not slobber right now. No slobbering.
You know, my knowledge is so limited in these areas that some of these black hole business, I don't even know whether that's what I'm reading is science or science fiction. You know, so like it seems too sophisticated for me.
Well, anything else?
Okay, thank you everybody for coming to my talk. I hope you enjoyed it. Have a good rest of your evening, and hope to see you at a future meeting.
I very
Thank
much
you.
enjoyed it.
That's great.
Thanks a lot.
Yeah. All right. And unless somebody else has something.